Hello, now today I start about biaxial bending doubly symmetric section. This design consists of AISCLRMT. Now start a design example. Example shows design a W section to serve as a crane support girder to carry a live load moment 301 feet without impact. That means when we consider impact, 20 or 25% impact must be considered in the design phase from the crane wheels. In addition, a moment of MF, M suffix F of 30 feet acts in the plane of the top flange as a result of movement of the crane back and forth between the support girders. This moment MF is based on a lateral force acting. That means MF is based on a lateral force acting on the top flange equal to 10%. That means total 20%. 20% total is 20% with 1/2 at each end of the lifted load and the crane trolley weight in accordance with ASCE 705 section 4.10. The moment MF about the y-axis is assumed to be resisted by one flange. This axis is y-axis. Y-axis is assumed to be resisted by one flange. In effect, this is to account for the torsional effect by using the flagellar analogy. The approximation of equivalent system as shown in figure 1. These are the figure 1. You can see Px is the axial load causes for Mx and Py causes for My. These are the two load and two moment. So system is called biaxial. But uniaxial, just one load, one moment. But two load, two moment is called biaxial case. And H is the center to center, flange center, top and bottom flange center height. H by 2 is the this axis is the centroidal or neutral axis is H by 2, and this force is transferred this one with an equivalent moment. These are the equivalent bending moment. And finally, this equivalent moment is transferred to point Py divided by 2, and this force finally transferred in centroidal or neutral axis. This force is called 2Py. That means if one flange force transfer to the center, just value is doubled, and actual loading force, figure A, actual loading force transfer to centroid, apply flexure analogy for torsion, force system for selecting section, so that stress point at A is the same as in C. That means this is the stress point, mainly stress required in flange section where load is applied. A is the stress point. Similarly, A is the stress point. Now assume this simple supported span. That means total span is known as simple supported, which length 24 feet is laterally braced only at the ends. Use load and resistance factor design LRMD and FY 50 KSI. That means a 992 still is used. Now approximate equivalent system for biaxial bending and torsion. Now go to the solution. Before start solution, I say of my viewers, please subscribe my channel and click bell icon. When I get another important topics for practical, professional and educational purpose, you can get easily. And if you interest my video, please like this. Now start solutions. The solution is computed in several steps. Number 1, that means A, compute vectored moments. In these moments divided dead load moments, live load moments, and including impact load with the live load. Compute factored moments using ASCE 7 LRFD load combinations. Estimate dead load moment. A dead load moment comes from ASCE LRFD manual and 10 keep fit. MUX is the ultimate moment in direction of X. 1.2 dead load plus 1.6 live load with 25% impact load. That means live load increases 25%. That means 1.25 total load with considering impact, and 614 keep fit using 25% impact increases. That means live load increases 25% due to impact. Now ultimate flexure load 1.6 into 30. This load is already given in questions. Now y directions, this load must be equal to double. So in biaxial case, 2 direction moment I can get this MUX ultimate moment in x direction and MUY ultimate moment in y direction. Now select a section. Now next topic is section selection part. Required SX. SX is area moment must be greater than or equal to MUX x direction moment divided by 5B flexural strength reduction factor for bending or flexure FY. FY yield strength plus similarly MUY moment in y direction divided by 5B FY into fraction SX SY. MUX already known, 614 keep fit, so multiply 12, get the value in inch. 0.9 value of 5B, 50 is the value of 5Y, plus 96 is the MY value, multiply 12 to get value in inch, divided by 0.9 into 50, and SX divided by SY, this fraction is equal to 6, and now get this value 320 per inch cube. And select section, try W24 into 131 section should be try for design, and this section as per manual AISC LRFD SX equal to 329 inch cube. So again calculate SX must be greater than this value. So SX 61412 similar way, and just put this value SX divided by SY equal to 6.2 and 322 inch cube. Now check strength. This section selected, after selection of this section must be select the strength of this section. Strength check, the yield limit state appears to be satisfied, however the stability limit state must be set, and the final check of all criteria should also be always be made. Now first check yield limit state criterion. Yield limit state criterion is simply FUN equal to x direction moment divided by x direction section modulus plus y direction moment divided by y direction section modulus. Just inputted in the value. Y direction section modulus comes from chart AISC LRFD, and this value is 44.1 KSI. This value must be less than capacity 5PFY. These are 45 KSI. So 45 KSI must be greater than 41.1 KSI. So this condition is okay. Second check, the lateral torsional buckling. These are the most important check of lateral torsional buckling limit state. In this state, 5BMNX must be equal to MUX. So this section, W24 131, that means depth of section 24. Now plastic moment of this section Fy Zx, Zx x direction section modulus, and 50 Fy is the yield distance, 5370 divided by 12, and get the value MP 1542 cubic feet. And now LP is the plastic point and 1.76 Ry root over E divided by Fy. E modulus of elasticity of steel normally 29,000 KSI should be considered. Now put the value of E and multiply it with 1.7, get 300, and Ry divided by root over Fy KSI equal to 300. Put the value of Ry found from the AISC LRFD manual 3.01 divided by root over 50. In this value is get in inch, so multiply 1 divided by 12 to get in this value in feet, and LR is 31.9 feet. This value comes from AISC table 32 section by ZX, this manual. And nominal moment, this is the formula of nominal moment. This moment is actually in this case, in this problem, is capacity demand. So Mn equal to Cb into Mp minus Mp minus 0.7 Fy/Sx into Lb minus Lp divided by Lr minus Lp must be greater than Mp. Now just put this value, use Cb in 1, and this value to get Fy 50, Sx 329 in this section 24 131 W sections, and 12 multiply just the value in value get in feet, and this value 605 cubic feet. This 605 cubic feet ultimate moment is phi into nominal moment. Phi is the flexural reduction factor. This value is eto cubic feet must be greater than. So this value obviously not greater than, is less than, obviously less than. This value is must be less than this value. So okay, so this value is less than MUX. This value is the capacity of the section. So demand must be greater than, demand must be less than capacity. So section is okay. Now use this section. Now use this section with Fy equal to 50 KSI. Thank you very much for watching my video, and again says, if you interest in my video and get learned about my video and get necessary unnecessary things of this video, please subscribe to my channel and click bell icon for getting next educational important video. Thank you.